So who all watched that great game last night, 18 innings? Who stuck it out? Hey, whoa, more than I thought. You know, wow. All right, well, anyway, the reason I mention that is I have always thought that statistics is one of the most underrated disciplines around. I always thought that statistics is one of the most underrated disciplines. I think you can get so much out of it. And where I first learned statistics was as a kid, doing all the baseball statistics. And I figured out how to do it and what they meant, and I started doing analyses on them on my own and yada, yada, yada. So that's kind of my background on statistics. Anyway, our speaker today will be talking about how to think like a statistician. Dr. Hank Ibser is a professor, associate professor here at Willamette in data science. And he says that the reason he likes statistics is because he gets to play in everybody's backyard. Statistics can be used for everything. So with that, I'll turn it over to Dr. Ibser.
Well, thank you, and thank you for having me. Since we're talking about baseball, I'll just say, like, the joke I've always made is that I much prefer to read the box score than to watch the game. So that's who I am, right? Sorry. So that's who I am. I like to look at the statistics more than like watch the thing. But that's a little bit of maybe how I think, right? And you don't have to think like me. I wanted to talk about this and make this my title to some extent, just because it leaves me free to talk about whatever I want to talk about in some ways, because this is sort of about my experience as a statistician, different things I've worked on, different backyards I've played in, and yeah. So I hope you enjoy this first hour. I thought I would talk a little bit more about kind of traditional statistics. So this is a little bit like how I was trained as a statistician. And then the second hour into sort of more modern, like where my interests have sort of evolved and where we are, I think, kind of as a world, and how statistics and data science and algorithms and generative AI can help and harm. So that's sort of the broad, big picture. As you see here, I'll talk briefly a little bit more about myself and about kind of my career path, academic path, and then a little bit about the history of statistics through description of a few statisticians that were prominent. And then I'll talk about public opinion polls for a little bit, and kind of weaving in a little bit of statistical methodology, techniques that are used to analyze data, a little bit about statistics and the law, and some consulting work I've done, and also about ways in which I think that statisticians think in some ways like maybe criminal lawyers think. And then finally wrap up with some discussion of clinical trials and how they're done. So that's, again, sort of like going sort of from the past and my past through this arc of how statistics is often used. Okay, so I am a professor of data science officially, so I have a couple of milestones to think about as how I got to this place. My dad was a physics professor, and I didn't realize how much I had learned about physics from him until I got to college and found it all sort of like obvious for about a semester or two. And then I felt like I didn't like all the stuff that you had to do that was messier than my math classes, which I really enjoyed. Friction, if you know what the Coriolis force is, things like that, where really seemed like, why do we have to deal with this kind of thing? And I felt like my math classes were just sort of more pure and abstract, and that was what appealed to me at the time. So I got into math, and at the same period of time, I've always enjoyed games of chance, and when I was in college, I played a lot of backgammon, I played a lot of poker, and I found this class in probability theory that I took my last year. And when I found out about it, I thought like, oh, it's a mathy class, maybe I'll like it, we'll see what happens. And then when I started taking it, I really found the problems to be just ones that I just loved. And so I sort of, this is my last year. I was still going to be a math major, but I kind of took as much probability as I could the last couple semesters that I was as an undergraduate. By the way, this all my education was at UC Berkeley. I was an undergrad there. I was a grad student there. And then I taught there for a while. And that made me think maybe I should go to grad school. And so I wasn't particularly directed at that time in my life. But there was a professor that, saw me in class and saw that I was really interested in it and suggested maybe I should go to grad school. And I thought in grad school, I'm going to study probability. But then when I was in grad school, I was in the statistics department, and they made you take some classes where you had to look at real world data and stuff like that. And then I found that that's what I was drawn to, that I wanted to spend my time solving problems with data. So I kind of shifted. I kind of got sick of, sort of theoretical proving theorems and things like that, and got into kind of more data analysis realm. There was one particular paper that I read at the time in a class, which was on race bias in the administration of the death penalty. It's a quick story about it. It sort of pushed me in a couple of directions. One was in terms of sort of criminal justice and ethics that will come up later. And then one was, again, thinking about sort of real world problems. So this paper looked at data from the 1970s, and I don't know if you're aware, the death penalty was for a 5-year period declared to be unconstitutional. And it was because it was being administered in a way that was biased, that black people were being executed more than white people, especially in the South. And so it was 1972 was the first court case that they decided, okay, it looks like this isn't fair, it's unconstitutional. And in 1977, several southern states petitioned, sued to bring back the death penalty. And they used data to make their argument, which was essentially that blacks and whites were being given the death penalty at the same rate for similar crimes. And the problem with and the Supreme Court agreed, reversed, brought back the death penalty. And there was this paper written at the time that looked at the data in kind of a somewhat a novel way, which was that you shouldn't just look at the rates at which people are going to death row. You should look at, based on race, you should also look at the race of the victim. And it turned out that, that in the South, mostly, black people were killing black people and white people were killing white people. And that the black offenders and the white offenders were mostly going to death row at the same rates, but when the whites killed black people, they were very rarely going to death row, and when the black people killed white people, they were very often going to death row. So there were these two things that were kind of canceling out, which was that if you murder someone, you're more likely to go to death row if you're black, and if you're murdering someone who's white, you're more likely to go to death row. And so those two things were sort of canceling. So overall, the numbers came out a certain way. So that example was really interesting to me, and it made me think a lot about kind of criminal justice and bias in this way. And I ended up writing my PhD thesis on the effect of increased imprisonment on crime rates. So if we put a lot of people in prison, which we did, especially during the 90s, we just about tripled the imprisonment rate. How much crime do you avoid? So that's sort of story of my arc. I guess I'm really talking about the statistics for a long time, part of my arc in graduate school. And then when I finished, I was a lecturer at UC Berkeley for a long time. Didn't do much research, was mostly interested in teaching, but occasionally did some sort of side projects, consulting projects. So that was, I was there till, I guess, just after the pandemic. And then sort of during the pandemic, my wife felt like we were spending, it was expensive to be in the Bay Area, and we were just sitting in our houses anyway. Maybe we should consider coming to Oregon. My mom was up here, my sister was up here, so we came here, and I taught at Reed College for a couple of years in the math department, so kind of like went a little bit back to math. I taught statistics within the math department, but sort of in a theoretical way. And I felt like I wanted to get a little bit back into teaching data analysis and things like that. And also during this time, partly when I was in statistics at UC Berkeley, but also at Reed College, I became increasingly interested in data ethics, which I'll talk about a fair amount in the kind of second half. And the effect that we have as statisticians on kind of like the world, and so I became more interested in that, and was not able to teach a class in that at Berkeley or at Reed, but Willamette had an existing class, so I was kind of excited to take that over. Here I'm a data scientist officially. So in my mind, the field of data science is a little bit like a rebranding of statistics. I feel like I'm not doing anything particularly different than I did as a statistician. There is a little bit more focus on kind of data visualization and communication of statistical methods, but kind of like the technical stuff is largely the same. There's also, I guess I would say, a little bit more computer science and coding, but as a statistician, kind of need to do that anyway if you're dealing with data. Okay, so there we are. So I wanted to just talk a little bit about the history of statistics, and part of this is my feeling like my discipline has, kind of warts, and some of the statisticians I'm going to talk about are, sort of maybe not great people, and they had important influence on the field and on science more generally, but I think it's good to sort of recognize like where some of it came from and what they were trying to do in developing these methods. So first of all, the kind of start was thinking about statistics as statecraft. So that's kind of the statistics word has that root, that Latin root in it, and there were high statisticians who were looking down on those who were just sort of table makers collecting data. So again, maybe I'll sort of mention baseball if you're familiar with the Moneyball story. So this is a little bit like the scouts not listening to the baseball like analysts that were using data just to think about evaluating players. And that was sort of the start of the field, was that there were sort of people that believed in governing and doing statecraft without using data or numbers, and that's sort of, they called it vulgar, to just look at the numbers. So that was sort of the start of things, and now we sort of, your common definition of statistics is around studying the collection, organization, analysis, interpretation, and presentation of data, and of course there's a lot of it now. There's just a tremendous amount all the time, as I'm sure you're aware. So yeah, we have to deal with it in some way. So a little more on the history. So Francis Galton was a half cousin of Darwin, and at this period he was very interested in heredity and how traits are passed on, and he was the first person who really used correlation and regression. So correlation, looking at the kind of relationship between variables, regression, trying to predict one variable from another and kind of understand the relationship between variables. And he was often touted as the founder of eugenics. So that's the sort of, dark side, right? So, his perspective on all this was that if you believe in survival of the fittest and that species get stronger through, sexual selection and natural selection, then what are we doing with the human race? Like, this isn't a good way to like run a species, right? So that's why it was the root of it was this kind of Darwinist perspective, and so he was out to show that these traits are inherited, intelligence and whatnot, and who should be the people that carry on the future, right? So that's is. I mean, I sort of understand the argument, right? I am not here to like talk deeply about eugenics, but yeah. So that was some of the most important statistical methods were developed by him for this kind of I don't know, low purpose anyway. So. Ronald Fisher was maybe, I guess, there are people that I've read articles about how he's the most influential scientist ever. Probably you've never heard of him, but he was the person who first used p-values, and so if you've ever heard of a p-value, that comes from him. That's maybe sort of the way that scientific research uses data, the sort of main way that that statistics is done. Most common thing that people do is to do a hypothesis test, look at p-values, which I'll talk about later. If you don't know what they are, totally fine. So that was one of his big innovations. He also worked a lot in experimental design, especially around agricultural problems, and kind of was originator there. He was sort of credited with doing the first hypothesis test in a certain sense, which was that he was at a tea. He was British. He was at a tea, and there was a woman there that said that she preferred her tea to have, I actually don't remember, I should have looked this up, to have the milk poured before the tea, or it may have been the tea poured before the milk. That's what she wanted, and he said, there's no possible way you can tell the difference. And she insisted, and he said, let's do an experiment. So he had her taste test, I think it was 25 cups. Some of them had been poured milk first, some had been poured tea first. And she didn't do that badly, which was sort of, this may be also the first example of what's called a type 1 error, a false positive, that she was able to do somewhat better than you should expect by chance. Not, she didn't get them all right, but that sort of, she seemed to, and I'll talk about later, like p-values are not perfect, right? But she was able to do like a little bit better than you expect by chance. So if you think about it in terms of probability, her feat was that she achieved something that maybe should only be achievable about 4% of the time. So might have been just random. I have like 2 points about him that are kind of blemishes on his career. One is that he was quoted by the tobacco industry for a long time in the 1960s as saying that there wasn't any statistical evidence that smoking was bad for you, essentially. So he was a big proponent of the idea, if you've ever heard this, that correlation does not imply causation, so that there can be a relationship between two things without there being a causal relationship. He had some interesting theories about how this might work. One of them was that people who are predisposed to getting lung cancer may have discomfort in their lungs, which is eased by smoking, so they're more likely to smoke. So maybe cancer causes smoking. In any case, he said, smokers have all kinds of other bad habits. They are more likely to drink, they have worse diets, they don't exercise as much. Who's to say, right? So it was in this period of time when animal research was done on the effects of tar, nicotine, and they, how you feel about animal research, they dissected the animals and could see that there was damage in the lungs. So that was discredited, but this is sort of considered to be part of the reason why it took so long to get Surgeon General warnings on cigarettes. So the other thing is he was also a eugenicist. So he was sort of in the same period of time, he was a Nazi sympathizer and believed that, white people are better than other people and they should have more children and all this. So, yeah, again, some amazing work that he did, and there were things that he did which were trying to use statistics to prove his theories. Okay, so Jerzy Neyman was the founder of the UC Berkeley Statistics Department, so he's sort of someone that people that, I wasn't there at the time, but people that were educated by him educated me, so I'm kind of a, academic descendant in some way. And he was the first person to formalize the idea of confidence intervals. I'll talk about confidence intervals a little bit later. He also formalized hypothesis testing. So Fisher and he feuded about how hypothesis testing should be done. Fisher believed that the p-value should be used in, I would say, a more nuanced way than Neyman did. Neyman believed that, so Fisher believed that you should have like shades of gray, that like the stronger the evidence you have, then the smaller the p-value. I'll talk about this more a little bit later, but this more kind of like gradual idea. And Neyman was one of the first ones who believed that we establish an objective rule, and that arbitrary objective rule has generally been that you want to have a p-value less than 5% in order to prove something. So again, I'll talk about that a little bit later, but he kind of like formalized most of the way that hypothesis testing is done today. He also formalized a lot of the ways that we do clinical trials today, and I'll talk about a clinical trial example a little bit later. He was responsible for this kind of specific sampling technique, stratified sampling, which is often used in public opinion polls. It amounts to, if you want a representative sample, you could just like pick a bunch of random people, or you could do something like make sure that the proportion of people that live in urban areas is the same as the proportion of people that live in urban areas in the population. So if we know things about the population, maybe we should sample separately from urban areas and rural areas and do that in a way that's proportional to the number of people in those areas. So that was an innovation of his that has been widely used for, as I say, a lot of public opinion polls and other purposes. All right, one more. This is John Tukey. He did early work with von Neumann on computers. He coined the terms bit and software. Bit is binary digit. I don't know if you know that. And he kind of liked to play with language. He was the first person to use box plots, if you know what a box plot is. He was very much into data visualization and concepts of data science. I've heard him called the sort of the father of data science. And that quote is from him. About the best thing about being a statistician is you get to play in everyone's backyard. Okay. Okay, so on to public opinion polls. So this will kind of tie into some of the things that we've been talking about. There's this quote that I kind of like: if you don't believe in sampling, be sure the next time you have a blood taste, make them take it all. That's from Nielsen, who is, Nielsen ratings. And so they were using, samples to see what people were watching. And this idea, I think, is really interesting because it's a joke, but also the thing with sampling is that, the thing about a blood test is you don't need very much blood because your blood is really well mixed. And so it is pretty easy to tell from a small blood sample what's going on in all of your blood. Sampling is a harder problem in that it's not easy to get everyone to talk to you. How you conduct the sample makes a big difference. So who you get to be in your sample, you want a sample that's representative of the population. But it's a much harder problem. So I agree with the sentiment to a large degree. Like, you can infer a lot of things about the population based on a sample, but it is a harder problem. Okay. Yeah, so we sample because taking it all isn't practical. Taking it all would be taking a census, right? So the United States does a census every 10 years, but it's hard, right? And you still don't get everybody, and the people that you don't get are known to have different characteristics from the people that you do get. And so you do have issues. And every census, some of the states sue the federal government because the federal government doesn't make adjustment for known biases in the data, and is known to undercount people that are unhoused and recent immigrants. And so since congressional apportionment is done based on this, and a lot of federal funding comes from this, states that have more undercount are disadvantaged. Okay, so a little bit, just a few definitions here, talk about public opinion polls. So just loosely, population is the group we want to know something about. Okay, so this may be like all US adults or something like that. It may be just registered voters. It may be different for different circumstances, but we want to know something about the population. The thing we typically want to know is called a parameter. So that could be the percentage of people that will vote for a candidate. It could be, whatever question you want to ask on a poll. It's going to give you some number, and the number you want is the parameter. The number you get is based on a sample. So you get a subgroup of the population that we know something about. What do we know about them? We know the statistic. So the statistic is the same as the parameter, but it's for the sample and not the population. And I have a little bit of a pet peeve with polling organizations, because pretty much anytime you read results from a poll, the results will be described as though this is the percentage of the population that believes a certain thing. And really, it's a statistic. It's a sample value. And I get that it's a little bit nuanced, and it requires a little bit of explanation as to what the difference is and how much variability there might be, things like that. But I feel like the public opinion polls generally treat the sample value as sort of the true population value. Okay, so we'll talk a little bit about the variability in there. I have a little example. This is a poll question that was done by Quinnipiac University. The results were October 16 to 20th. They took a random sample of 1,327 self-identified registered voters, talked to them on the phone, and asked them this question, right? So the answer is that 45% said Republicans, 39% Democrat, 11% equal, and 5% didn't answer or didn't care, whatever. They didn't give a response. So the parameter that I'll talk about is the percentage of registered voters in the United States that would answer Republicans if you asked them. So the statistic is the 45%. The sample is the 1,327 registered voters that they actually talked to, and like I said, so the population is the registered voters. So that's something you might want to know for, thinking about if you're a Democrat or if you're a Republican. You might look at that number and try to decide whether or not you want to give in to the other side and try to end the shutdown. The fact that those numbers are pretty equal leads to a bit of a standoff, as we see, and there is some variability in that number. Their reported margin of error is plus or minus about 3.5%. So that is called a 95% confidence interval. I'll talk more about what that is later, what that means. But that's kind of like how the results are often reported, and the margin of error appears sort of maybe low down on the web page, or maybe you have to click on something to get there to figure that out. So there is some variability. This is not a super big poll. It's kind of an industry standard to do a poll that has a little bit more than 1,000 people in it. The more people you ask, the more expensive it is, of course. But the more precise your results will be. Okay, so that's a little example to sort of frame our discussion a little bit and give you something to think about. Another quote I like, that essentially all models are wrong, but some are useful. And I'll talk about a statistical model in just a bit. George Box has these two quotes that I kind of like. So statisticians, like artists, have the bad habit of falling in love with their models. And this is what we mean by one example of a model, that a statistic, the sample value, is roughly equal to the parameter, the population value, but it might be off. And the two ways that it might be off are due to sampling error and due to bias. So the sampling error is sort of randomness. So the statistic we're using the statistic to estimate the parameter, and it might be off for these two reasons, sampling error and bias. The equation might feel like it's written backwards because you might want to, you might think like, well, what I really want to know is the parameter, and so I should write the parameter as being equal to something based on the statistic, right? The idea of the model is that this is how the data is generated, right? So from a statistician's point of view, we're interested in thinking about a model for like, how did we get this statistic, and what's the randomness in the process of getting that statistics, or what's the possible error in that process. So, a model, the idea of a model, like an airplane model or something like that, is a representation of some real world thing that has some of the characteristics of that thing, but is not the thing, right? So that's the sense in which I think George Box is saying that all models are wrong or some are useful, that a model airplane might be useful to explain how an airplane works to someone who's never seen an airplane, but you shouldn't then rely on the model as some sort of truth. And this is a relatively simple model. Models are, kind of a foundational thing in statistics. I remember that when I was working on my PhD thesis, the first question, whenever I was looking at data, my advisor would ask me, well, what's your model? So it's sort of a thing you always sort of have in mind, like, what's your idea of how this was generated, how this data was generated? What variables are relevant in how this data was generated? And kind of understanding that process is a lot of what I think traditional statistics is about. Okay, so sampling error, bias. So sampling error is random error based on the sampling process. If you got a different sample, a different set of 1327 people, you'd get a different result, a different statistic. So this is, if you're familiar with the distinction between precision and accuracy, this is about precision. If you take, if like 10 different polling organizations all took 10 different polls, if their estimates are precise, then they should all be close to each other, okay? The issue of bias is systematic error. So for example, if younger people are less likely to answer the phone for an opinion poll, if non-native English speakers are less likely to respond when they get a call about a poll, you don't get their opinions, and then this might be a problem that affects all of the polling organizations. So all the polling organizations may have an accuracy issue that their estimates are all off in the same direction for the same reasons, and they may not have a way of detecting that. Okay, so statisticians are good at the sampling error part of it. We know a lot about randomness and probability and how these things work, but the bias is a little trickier. So public opinion polls have had issues. Somewhat famously, the 2016 presidential election, a lot of the polling organizations were predicting that Hillary Clinton would win, and got it wrong. And the few statisticians and pollsters that were kind of like raising red flags were concerned that in the polls, it seemed like they weren't getting enough voters that might be voting for Trump, and especially weren't considering voters that hadn't voted before that might vote for Trump. So they kind of underestimated the proportion of certain groups that would come out to the polls. But yeah, so it's a tricky thing to sort of think about that part of the bias, or how the bias is likely to affect things. Okay. So, a few kinds of bias. So selection bias arises from how you chose people. So if you're calling people on the phone, not everyone has a phone. Some people are going to have a cell phone. Some people can have a landline. You want to make sure you do both. The Quinnipiac poll does both, so they're addressing that issue. But yeah, so in the selection process, you want to try to make sure that the people that you select, that you call, are representative of the population. Once you call them, you can have non-response bias because not everyone will respond to you. So they may not, answer at all, or they may hang up once they realize that you're a public opinion pollster. If it's you would also include in this, if you have a landline, if you're not home, that's sort of included. They selected you, but they didn't get a response from you. So that's part of non-response bias. So it's a way in which, again, there can be systematic errors. And the third main kind of bias that people talk about is response bias that may arise because of the context or sensitivity of the question. They maybe don't want to share their opinions if they feel like their opinions are controversial, whatever. Generally, so there is one other issue with the 2016 election that some pollsters thought that there might be what they called shy Trump voters. That's not my impression of Trump voters, but they thought at the time that the people that were voting for Trump may be hesitant to say that to a pollster. The research on that is a little bit mixed. That seems to be not really a thing. But anyway, that was kind of a theory at the time that was an explanation for why the polls might have gotten it wrong. Okay, so back to sampling error. So I'll talk a little bit about randomness and probability. So if there are only two main responses, and in that poll that we were just looking at, they only offered two main responses. Do you blame the Republicans or do you blame the Democrats? The people that said equal volunteered that information, and they recorded that response as another response. But if we consider just two main responses, a public opinion poll is kind of like flipping a coin over and over, but you don't really know the chance of heads. So you might be interested in figuring that out. Oops. Okay, so we can study coin tosses and sort of think about the randomness there. So I did a little simulation of 100 fair coin tosses. I repeated that simulation 10,000 times. You get this picture. Don't worry about the axes. I know they're too small to read, but just the shape. So this is, looks roughly like a normal curve, if you're familiar with a normal curve. There's statistical theory, probability theory, that says that it should look pretty much like a normal curve. Yeah, so this is simulation. You can see a little bit that if you look at the top 3 bars, that it's not quite symmetrical. There is a little bit of randomness going on. But anyway, that's a simulation. So this is theoretical. So I tried to match those up so that I could go back and forth and show you that they're pretty much the same. This is sort of the theoretical distribution of what you should expect for coin tosses, and I did superimpose a normal curve on there, so you can see that it is very close to that. And this is with, a known coin toss. So by studying the sort of what I consider to be kind of the forward process of I know what the coin is, I know it has a 50% chance of heads, maybe it gives me some insight into the kind of real world problem of I'm tossing a coin where I don't know the chance of heads. But I can still think about the variability and study the variability in this known process. Okay, so the idea of a confidence interval kind of takes into account this idea that, you have some randomness that you kind of can quantify, measure in some way. Again, this was Jerzy Neyman's, one of his contributions. And if we go back to our model, we're thinking about sampling from a population. We want to estimate the parameter based on the statistic, and we consider the statistic to sort of be generated randomly, but it's based on this unknown parameter, right? There's some like percentage of people in the country who, if you ask them, would say that they blame the Republicans. And we don't know that. So it's not exactly like a coin toss, but we think it's probably, fairly close to 50%. 45% was the sample value. So we can think about the variability in, say you had a coin that landed heads 45% of the time. We can like do a simulation or do some theory, get an idea of the variability based on that. So we know something about the precision of the estimate from studying the coin tosses, or sort of things that are like coin tosses. And the typical way to represent that sampling error is to think about the margin of error, which usually corresponds to what's called a 95% confidence interval. And I'm just going to zip back really quick to this. So this, for 100 coin tosses, 100 would be very small for a poll. You wouldn't get a very accurate result. You can see that for a fair coin, maybe you can't see, down on the x-axis, the center is at 0.5. The point to the left of that is 0.4, and the point to the right is 0.6. So about 95% of the time, it turns out you get between, if you were to toss a fair coin, you get between 40 and 60 heads. That wouldn't be very good for a poll, right? So if you had an interval which was, I think the percentage of people who blame Republicans is something between 40 and 60%, that's not very useful, right? So you definitely want to do a sample that's bigger than 100. And as I said, they did 1327 in their poll, and that gives what's called a 95% confidence interval of about plus or minus 3.5%. Still not like really, really precise, but at least maybe, I don't know. Would you use it? I don't know. If you're going to use it to make decisions based on, like, if you're, again, a Republican or a Democrat in Congress and you're trying to decide whether or not you should give in to the other side, maybe that's good enough. There are a lot of different polls being done right now on this issue, and what is typically done is that someone aggregates the polls, so the different organizations that do that aggregation, and then you get a little bit more precision by taking into account many polls rather than just one. Okay, so if we go back to our model, so statistic is equal to parameter plus chance error plus bias. Again, we want to study coin tosses to get an idea about the chance error, and it's based on the idea that if we can say something about the likely size of the chance error, then we'd like to find an interval that's likely to contain the parameter. So that's the kind of way that statisticians think about this thing. I'll just make a kind of like small tangent that there are, like most statisticians would say that the parameter is some fixed number that is, we don't know it, but it's fixed. And a kind of slightly looser position, if you've ever heard of Bayesian statistics, maybe a couple of you, I don't know, is to think about the distribution of possible values the parameter could have and to think about the randomness in that part of it. I'm going to focus on the kind of more traditional viewpoint, which is that the randomness is just in the statistic, and we want to think about then like finding an interval, again, that's sort of likely to contain the parameter. So this is the metaphor I like to use, is that constructing a confidence interval is like tossing a ring and you're trying to cover an invisible stick. So maybe here's my parameter. It's invisible, but I'm tossing a ring and trying to cover it. And I know from studying coin tosses how precise my ring tossing procedure is, but I'll never know if I actually manage to cover the invisible stick, right? So that's the way I sort of think about the process of making a confidence interval, is that, the bigger the sample size, for example, the more precise my ring tossing procedure is. And I can construct a smaller confidence interval, maybe get a more precise idea of where the invisible stick is. So yeah, that's this comment here, more precise the ring tossing procedure is. And usually, like I won't say that my ring is more likely to cover the stick, but rather that having a bigger sample size allows me to have a smaller ring and still maintain that idea of 95% confidence that, like, 90, one way to think about it is if I toss 100 rings, I expect 95 of them to cover the stick, right? Okay. Yeah, so for the original poll, they said sample size is 1327, margin of error is plus or minus 3.5. And what they're giving, without calling it that, is a confidence interval. So that's a 95% confidence interval, is that the percentage of all registered voters who blame Republicans is 45% plus or minus 3.5%. So I guess the left side would then be 41.5, the right side would be 48.5. So that describes sort of the size of my ring. And, I'm pretty confident that that includes the true parameter. But, it's not a sure thing. Okay, so that's a bit about confidence intervals. Thanks. So Quinnipiac, like many polling organizations, adjusts their results based on demographic data. They use gender, age, education, race, and region. So if they get too few people with particular characteristics compared to census data, they'll weight those responses more heavily. So, for example, if 18 to 24-year-olds show up in, 10% of people, maybe that's high, maybe 5% of the people in the poll are aged 18 to 24, but in the population it's 10%. They'll essentially double those responses to make it proportional to what they think should be in the population. Education is something that was generally added after the 2016 presidential election, that this is a way of accounting for one way of accounting for the Trump voters, that they typically were, and I guess are, people with less education, and that they should be adjusted accordingly. Those people are typically not responding to polls, and so they should be, their opinions should be sort of amplified if you want to be able to predict more accurately. Okay. Oops, I can copy that twice, sorry. All right, so I'm going to talk about hypothesis testing a bit. This is, like I said, maybe the most common thing that's done in science to reach conclusions based on data. And rather than trying to construct a range, a confidence interval that's likely to contain a parameter, the logic of the hypothesis test is to assume a certain value and then see if the data is plausible given that assumption. So this is a little bit like assuming that defendant is innocent until the data is sufficient to prove guilt. That the kind of default is like, there's sort of nothing going on, but if the evidence shows otherwise, then we're going to conclude otherwise. So what are those hypotheses in the hypothesis test? Well, the first is called the null hypothesis, which is sort of there's nothing going on besides just randomness. That would say that a vaccine is ineffective. It didn't do anything. And in my little, legal analogy, I guess, it means innocence. The alternative hypothesis is that the data could not plausibly come from the model based on the null hypothesis, that there must be something wrong with the model, which might be that the vaccine works, or that, kind of someone's guilty. So that is usually what you're sort of trying to prove based on the data. And if you sort of fail and the results in your data could have just been sort of random, then you don't really have anything to publish or anything to say. So this is often a critique of this method, is that it results in people just working until they're able to reject the null hypothesis. This was part of Fisher's argument against Neyman, was that if you give everyone this objective rule, everyone's going to do it, and no one's going to understand it. So I think Fisher had a point in that way, but it's mostly what people do when they do science. So you're trying to decide at the core whether or not the data could plausibly have been generated by that model. All right, p-values. Just briefly, we define a p-value as the chance of getting data like we got, or something more extreme, given that the null hypothesis that it's just kind of random, innocent, whatever, is true. So to make that a little bit more real, I'll go to one more slide after this, but this is kind of how Fisher viewed it, is that the smaller the p-value is, the stronger the evidence is against the null, and he preferred to view it in what I would say is sort of a nuanced way. Neyman and people that worked with Neyman wanted to have some objective process, and so they wanted to have like a line where, okay, if it's past this line, we conclude this. If it's on the other side, we conclude this. That has some issues with gray areas. So as I said, with the T example, we had a p-value of about 4%. Could have been random, right? And I guess I believe that it was random. I believe that she got lucky. But she would have been able to publish her results, right? That's sort of the industry standard, is if you get a p-value less than 5%, you conclude that it's not just random, that there's actually something going on. Okay, so I'll talk a little bit about a COVID example. There was a large clinical trial in 2020 that had these really big groups. And in the treatment group, the vaccinated group, there were 8 cases of COVID, and there were 162 in the control group that didn't get a vaccine, got a placebo injection. And the way that this is treated is that it was about 95% effective. 8 turns out to be almost exactly 1/20th of 162. So that's how they determined the 95% effective, is that the 5% that are not effective are the 5% that got COVID in the vaccinated group. And they have a confidence interval for that. So that showed that the vaccine was effective. A hypothesis in this testing case, I actually didn't bother doing. The p-value would be extremely, extremely small, right? The chance of this happening at random is really small. One way you might think about it is you might think, okay, we got like 8 plus 162 is 170 total COVID cases. And if the vaccine didn't do anything, you'd sort of expect about half of them to be in the vaccinated group and half in the placebo group. Well, if you toss a coin 170 times and you only get 8 heads, you sort of know there's something wrong, right? So you don't really need a hypothesis test. The chance of that happening would be astronomically small. Okay, so quick review. We talked about confidence intervals. This is a review of the statistics content. Like throwing a ring, trying to cover an invisible stick. A hypothesis test gathers data as evidence. Again, we assume no effect, innocence, until there's enough evidence to prove guilt, like the vaccine works or whatever conclusion you might be trying to reach. Okay, that concludes part 1. Are there any questions? Thanks.
Good morning, this is Cassia. I'm over here in the second row. Thank you.
Hi.
Going back to your polling and the aggregation of results, I've always been puzzled by that. Does it mean that every poll has to have the same questions in order for it to be valid? Or can they use different questions? And how does it work with the question when it's 1 through 10 is an answer, or sort of, maybe, possibly, definitely is an answer?
Yeah, it's a good question. So whoever's doing the aggregation has to make a judgment call as to whether or not they think the poll questions are comparable. For a lot of, definitely for polling for elections, they're just the candidates are the responses. So it's a lot easier to aggregate results. If you're going to aggregate results for something like this, yeah, you need to have pretty similar wording to be confident about it. And definitely, statisticians argue about that stuff. Yeah.
Over here.
I'm Mark, and I read a poll, and I don't know if it was a Quinnipiac or a Gallup or whatever, and I went to the source data explanation, And I got down to the point where they said that they had randomly sampled 1,239 people, and it was 36% were landlines. Now, only 27% of the households in North America have a landline anymore. I mean, my neighbor up the street is the only guy that I know, and he refers to me as youngster, and I'm 70. So, how do they address that skew? You'd subtract out, and then that's a different vector on the frame of the sample.
Yeah, so there are other polls that are done to try to estimate what percentage of people are using landlines and cell phones. And there's a trend, right, that we're losing the landlines. And the results from their estimates may lag to a certain extent. A lot of the organizations will try to make additional adjustments. So like they do for gender and age and all these other things, if they feel like what they actually got does not match the population, which is also based on a poll, that's also estimated based on a different poll, then they'll make an adjustment. Mostly the thing that people are comparing to is what's called the Current Population Survey. It's done by the Census Bureau. Those results are, I think, good, but yeah, not perfect. So it's a reasonable concern. And response rates for polls are pretty low. They're often under 10%. So it doesn't take very much to skew them. Yeah. Thanks. Yeah. So have time for one more question, I think.
Hi, this is Debbie. The news this morning that the Attorney General of Texas is going to go after the Tylenol drug as being not just, that there's a correlation. And I'm wondering how many folks like you will be called upon to interpret data results and what should be looked at to see how legitimate this claim is.
Well, I guess I have to say I haven't looked into it. I don't know if there is any reasonable evidence. I don't think that the Attorney General cares. They're not talking to scientists, I think. So, yeah. Okay, well, thanks. I guess we'll take a little break and then restart. Thanks.
We'll come back in 10 minutes at 11:10. I also wanted to, I forgot to mention when I kind of gave the introduction that Dr. Ibser also plays alto sax and electric bass or something like that.
That's right.
Yeah. So it's I find it kind of interesting. Several of the people that we've had here in the sciences and the STEM disciplines have also, played instruments and been pretty good musicians. So anyway, here we are for the second half.
Thank you. I've always sort of thought music in one way exercises a different part of my mind that I don't get professionally, and also that it is sort of math over time when you do music, both in terms of rhythm and tempo and in terms of notes and whatnot, the relationships between things. Okay, so part two, I'll touch on these kind of, maybe more modern topics, data ethics, politics, artificial intelligence. I guess not necessarily in that order, but I'll just jump in. So I wanted to say a little bit more about me in the context of ethics, and and this is actually, bringing up the music, this is another way in which I feel like there's part of my mind or identity or whatever, what I'm interested in, that is not so kind of mathy. And I was particularly interested in data ethics before COVID. As I was talking about before, like the example with the race bias and the death penalty. That's something that's sort of, been a little bit of a thread for me, that I've been interested in kind of using data to shine a light on ways in which we have social inequity and various ways. And there was a book that came out called Weapons of Math Destruction in 2016. And it was written by someone that actually got their math degree from Berkeley also, and she was interested in how algorithms were used in ways that are harmful to society. She was working for a hedge fund company in 2007, 2008, and kind of saw what happened there, and using algorithms in ways that were profitable but had serious consequences that were sort of not unpredictable in a lot of ways. And the fundamental mistake they made was that they were packaging risk in a way that assumed that it was independent. And when things happened simultaneously for a lot of people, then the house of cards kind of fell down. And that was sort of the modeling error, the kind of mathematical, I would say, error that was sort of made in that process, was in that. Anyway, so she wrote a lot about, in her book, different ways in which algorithms that we use, the way that we use data, produces consequences that are not fair in a variety of ways. So that kind of, was interesting to me. And I also, in the Berkeley Statistics Department, we observed that we had the lowest percentage of underrepresented minorities of any department on campus. And we're curious as to why. And I kind of thought that this idea of kind of like shining a light on kind of social justice issues might be a way to attract people to the discipline that might not recognize that this was a tool that could be used for social good in some way. So yeah, sort of my interest there. I said before, largely the move away from my job at Berkeley was instigated by my wife that wanted to get out of the area, and I applied to this job at Reed, and as I say, taught there for a couple of years. But one of the things that, I don't know, maybe a little bit sad there was that the department didn't feel like that was the place to be teaching a course in ethics. And there are a lot of I really like that Reed exists. I think that it's a really interesting place, and for me, I felt like the department was a little bit more focused on proving theorems and getting students ready for grad school, and that wasn't quite what I wanted to be doing. So anyway, I was really pleased at Willamette. There was an existing course in data ethics, which I've taught 7 times in 5 semesters. I'm teaching 2 lectures of it right now. And my third class is my other love, and I'm teaching a course in probability. But that course is something that I feel like is really evolving rapidly. The issues that we're facing in data ethics are, I think, really important to how our society operates. And yeah, our little Willamette motto, not unto ourselves alone are we born. Okay, so apologize if you can't read this. I know the words are a little bit small. I'll talk through it. This is the idea of a data life cycle. And, I kind of touched on this a little bit in talking about like public opinion poll, how there are kind of like issues in data gathering and things like that, sampling. And I'll kind of break this into what I consider to be three main phases. My 1 to 3 is the first 3 wedges in the pie. So this is, if you can't read, I'll read it now. So the first 3 things are generation, collection, and processing. So this is ways in which we get the data. And I was just mentioning to someone during the break, like the idea that data is created, not discovered, that we have to have an active role in what we decide to gather, what information we try to get from it. And usually people have a question in mind when they are gathering data. Not always. Sometimes you're just kind of gathering data because you're curious, you want to see what you find. But usually people have a question in mind. They often have an answer in mind as well. This is a quote I like: "Raw data is an oxymoron," and then this idea that you can't have data, or we sort of can't observe data that is not affected in some way by our gathering process, how we got it, what we decide to look at, what we're observing. So I think that's important to recognize. In my data ethics class, this is one of my fundamental things that I talk about, is that, if you're going to be a data scientist, you want to be aware of ways in which you introduce your own bias into the process through this data generation part. Governance. This is, so 3 is processing, which is, I feel like, kind of a bridge between acquisition and governance. So processing, storage, and management of data. So I think we're all sort of aware of, there are data breaches, there are data privacy issues. You don't really know how your data is being used by who. You click I agree on user agreements without reading them. All right, so these are all, I think, serious issues. I would say that, in this way, the system is kind of broken. We don't really have adequate both education about how data is being used and understanding about it, and also I think this is an area that really needs some regulation, and it's not happening. Okay, so yeah, that's that. Oh, and incidentally, I just want to say the second of my half of my talk is more depressing. So just be aware of that going into this. Okay, so the last 3 steps in this, so this is from the Harvard Business School, is this graphic, but so that their last 3 things are analysis, visualization, and interpretation. This is, I think, is what kind of the heart of what a statistician does, data scientist does. And I've labeled it storytelling to kind of emphasize the idea that it is a very subjective process, right? How you do data analysis, what you choose to show, visualize, how you show it is, based on whatever bias you may have. And then finally the interpretation, how you're kind of going to spin the results in a particular way. And that storytelling is often an iterative process that you analyze the data in a particular way, and it doesn't agree with what you thought or what you believe, and so you analyze it a different way, and you try to, shape it to your purposes. There's a quote just occurred to me, I didn't put it in here, but if you torture the data enough, it will confess, is another quote I like. Yeah, so you can, part of the reason I like that quote is that just like if you torture someone enough, you will get the answer that you want, but you can't have any confidence in the validity of that answer anymore, right? So there's that. And then another quote I did throw in here is, most people use statistics like a drunk man uses a lamppost, more for support than illumination. So again, often people will have an answer in mind when they are going to collect data. So they'll collect the data in a way that will likely be able to answer their question in the way that they want it to be answered. And throughout the process of how they process that data, how they deal with there are always judgment calls about like, how do I deal with these particular cases that are a little bit like the others? How you deal with those decisions will often kind of affect the end result. Okay. So I have some graphics here. You don't need to worry about reading any of the words. But this is a story that was about this Amazon hiring algorithm. And I have links on a lot of these slides to the original thing, which I will share, the slides or whatever. This algorithm that they used, they didn't use it for very long, but they used an algorithm to evaluate resumes. This is what we would usually call machine learning, and it is a process where the learning part of it, and there's a lot of anthropomorphization of a lot of the methods that are used in statistics. It's not really learning, but you are going through a process where you are using data to train a model to be able to predict something. So what they're trying to predict here is, will this person be a good employee? And what they're using as data is, what are the people that are working here right now, right? What are their characteristics? And we want to hire people that are going to match those characteristics. Resumes for current employees were used to train the algorithm. Maybe not surprisingly, women tended not to make it past initial screens for technical and managerial jobs because there weren't very many women working in those jobs. Part of the problem here is not just that. So you might think of this as like, okay, the problem is that we're going to perpetuate whatever biases exist in the workforce now. It's actually worse than that. You do have a way of perpetuating whatever inequity is involved. But it's true, if the data used to train the model are biased, then the new hires will tend to be biased in the same way. But the models will tend to aim for the center of the distribution of whatever employees are there. So you tend to even more reduced diversity. So I kind of imagine this as like kind of a cloud of employees based on whatever variables you can sort of imagine, like, whatever variables you want to measure on the employees. And what the algorithm is going to do is sort of try to get people that are like the person at the center, or like some typical person. And so you'll not only kind of perpetuate whatever inequity exists, but you will, as the model progresses, tend to make the people working at the company even more homogeneous based on whatever variables you're using, right? And then you're going to use those people to train the next generation of the model, right? So you get this feedback loop where you just will tend to reject more and more candidates that are not quite like the people that are working there currently. A lot of hiring is done by word of mouth and who if you know someone there or whatever, and that also is sort of problematic, that you kind of tend to hire people that are like the people that are there. I feel like that part is a little bit more understood, but people kind of think that the models should be unbiased. They're just using data to predict something, but it actually can tend to be worse than having humans make decisions. And as I say, there's this feedback mechanism that will tend to happen. And this is an example, right? This is a thing they didn't use very long. They recognized the issues, but there's an article this month in the New York Times that said that about 95% of employers now use AI to filter or rank resumes. So generative AI. Let me say, I guess, a word about the term artificial intelligence. Again, there's this anthropomorphization. I think intelligence is not really a good word to use here. Statisticians and computer scientists have used the term artificial intelligence for a long time to cover a variety of methods. And really what we sort of think of as generative AI, as chatbots, ChatGPT, whatever, is what statisticians and computer scientists would call generative AI. But yeah, I'll use AI the way that it's commonly used. And so when I say AI, I'm usually referring to generative AI, but in this case, AI is, I think, used a little bit more broadly. So you're using some kind of an algorithm. You're not like necessarily putting the resumes into ChatGPT and asking who to hire, but you're using some kind of like algorithmic training process to decide how you're going to rank the resumes. And so, part of the problem here is that, so there's an underlying problem that these companies are trying to solve, and the problem is that they have lots and lots of resumes, right? And that's getting to be more and more a problem because, people are applying to jobs relatively easily on a lot of platforms, and they're applying to a lot of jobs, and so there are a lot of resumes to look at. So the employers would like a way to cut down the number of resumes that they have to look at. And so this is a quick way to do it. I would sort of argue that it would be better to do it randomly. The things that they're doing are not, do not seem to be associated with job performance when they're doing this kind of filtering of resumes, and that it will tend to hire people that are just like the people you have. I mean, I think, apart from whether or not you think that diversity is a worthy goal, I think it is worthwhile for employers to have different opinions, different perspectives, and that you have a stronger company, a stronger product, if you have people that don't all agree with each other about everything. Okay, so it's that. Okay, another example, predictive policing. Predictive policing is sort of similar to what you might think of as racial profiling, but it's typically geographic. So you're trying to find areas or neighborhoods where there's crime, where there's likely to be crime. And you don't have crime data. So you have arrest data, but you don't generally have crime data. And so the problem is that where you send police, you will tend to arrest people. And again, you get this kind of feedback loop. So you predict crimes based on arrest data, and then that existing arrest data may be based on over-policing of certain neighborhoods. And even if it's just a little bit, right, then you tend to make more arrests there, which you feed into your model, and then conclude that there's more crime there, and so you send more police there. And so that feedback process, kind of similarly to the algorithm, the Amazon algorithm, is that you tend to get feedback. So in addition to that, the parole decisions are made based on estimates of recidivism. So if people are likely to reoffend, if they're going into a community where they perceive a lot of crime based on arrest data, then they may not release people because they're afraid that they're going to recommit crimes. So those parole decisions are also affected by this kind of feedback loop. Which I sort of said already, but yeah, so it's in that Amazon hiring example, that problematic data is fed into an objective process, right? That creates a harmful feedback loop. And so, we want to pay careful attention to the downstream effects of using statistical methodology. And that can help to avoid these problems, but typically, like I say, the effect of the algorithms is to tend to amplify whatever existing biases there are. Okay. So I wanted to talk a little bit about generative AI and search engines, and news feeds also. These are all situations where the algorithms being used are kind of black box. They're not transparent. It's very difficult to try to figure out why things are the way they are. As a statistician, again, I like to try to make models and try to think about I have this outcome variable. What are the variables that I think are useful for predicting it? And in my modeling process, I would like to get estimates of the effects of these different variables on the thing I'm trying to predict. How much does this variable affect that variable? And in particular, you might be able to do things in a kind of traditional sense where you can get an estimate of how biased the model is. Like, you can look at, how much more likely are women to get hired at Amazon, or less likely are women to get hired at Amazon compared to men. And for the predictive policing, you can get an idea of protected classes based on race or whatever. It's very difficult to do that with these black box algorithms, with generative AI, search engines, news feeds. It's very hard to tell why you're getting the results that you're getting, and then to try to measure like what's the bias and why. Kind of these questions are pretty hard. So the part of the problem, there's a word that's been coined called techno-chauvinism, which is sort of the idea that you believe the technology before you believe a human, you believe the algorithm. And these algorithms, they sort of have this semblance of objectivity, but they are trained in ways that are going to reflect the bias of the data, and also the bias that the creators of the algorithms might have. And sometimes that's intentional, and sometimes that's not intentional. One of the links I have on here, I didn't write it up in the slide, but there's a Bloomberg study that was done on stable diffusion, if you know what that is. It's used to generate images. And they did this research where they asked to have generated 100 pictures of this kind of person. And some of it was occupations, but actually mostly it was occupations. And they found that, again, you have this amplification. So one example from that is that about, I think, 33 or 34% of judges are women, but in the pictures that were generated, 7% of the images were women. So again, you have this like idea that the algorithm is trying to aim for the center, for the typical, like what they consider to be, typical. So anytime there's like a minority person or whatever, they're going to tend to get underrepresented in the output. And that's true throughout all the things, right? So that phenomenon in a search engine is that you tend to have minority viewpoints won't kind of show up. So this is this point. So our input, what we take in through news feeds or, searches, whatever, anything you look at through generative AI, you'll tend to find things that are, sort of the more common opinion. And the minority viewpoints and speakers will tend to get drowned out. And misinformation and clickbait may also be spread disproportionately if it's, something sort of becomes viral or whatever. That process, again, sort of governs like what we all take in, right? And it leads to more polarization in what people see and what people view as sort of truth and fact and things like that. This is something that I think is not really considered that much. You sort of like, you do an internet search, you sort of feel like, you get reasonable information, and it's tricky. There's not an easy way to fix it, right? One thing you can do with generative AI is you can explicitly ask for, other viewpoints or whatever it is. It's a little bit harder with a search engine, but you can sort of like, you're essentially doing a little bit of your own retraining of the algorithm when you do something like that. You can also do that with your news feed, right? You can look for things that you wouldn't ordinarily look for, and you'll get, the algorithm will kind of update and give you more of that stuff. You don't know, kind of behind the scenes, if the person that is controlling the algorithm has other interests in mind, that they'd rather have you see this. So that part of it is a little bit tricky, that you need to have some trust in whatever the algorithms have in mind. And that's one of the strong arguments against TikTok, right? Having Chinese control over the algorithm and having it proprietary, and we don't know what's in it. We don't really know what kind of content they're going to want to have people see. Okay, AI-generated content in the same sort of way as with the other algorithms, right, can create a feedback loop. That's sometimes referred to as slop. I've heard the generative AI referred to as a B- machine for everything. That like it does a bunch of stuff, like okay, but I think there will be, you know, consequences for people that are, you know, having creative output, art and writing, things like that, where if consumers don't care, like if you don't care if you're watching a show that was written by AI, then you're gonna, like you broadly, right? If we as a society, maybe I should say, are okay watching things that are sort of, you know, B- level content, derivative, not that original, then that's what will be fed, right? It'll be cheaper, whether it's completely AI generated, right? And the video and everything, or maybe just the scripts are generated and then you have actors, you know, acting, actually doing the thing. That's part of what went into the writer strike a few years ago. And I believe that was in 23. And one of the concessions they got was that AI would not be used to generate content for the duration of the contract, which is up next year. So I'm curious, I'm sort of watching to see like what will happen next year. Will they be able to maintain that or not? And one of the main arguments for the writers is that one of the main sources of revenue for writers is that they come up with an idea for a show and that show gets picked up. And the writing of the show also generates income, but if you have an idea for a show that gets picked up, that's a lot of like, you know, you've really struck it rich. And it's relatively easy for an executive to say to generative AI, come up with 100 ideas for a show and pick one of them, right? You know, go through and say, yeah, you know, this is seems like a reasonable show. Now I'll go hire some writers to fill it out. And then you've kind of not given the writers an opportunity to get that payday. And so I guess I'm really curious about sort of what happens in the next few years with that kind of situation. And a lot of the training data for AI is, it's hard to tell how much of it is copyrighted, right? It's hard to trace the intellectual property and to sort of say, and there's an argument made by the developers that, you know, all content is derivative of previous content in some way. So, you know, whenever you write something, whenever you produce art, you may not be like directly imitating something, but what you do is kind of reminiscent or affected by the things that you like and that you have done. And there's not much regulation, right? So it's hard to keep track of. And like California has this year done more in regulation. The EU has done a fair amount in regulation. But yeah, it's mostly they can do what they want at this point. So I do think we need to have some greater transparency in the way that data is being used, especially this kind of copyright issue. And yeah, so that's the first phase. And this is based on a talk that I gave. This next part, the federal data removal, is based on a talk that I gave in March. So I left it in the slide format it was in. So that's why you have a slightly different format. This was, I've updated a little bit since then, but mostly this is talking about things that happened recently after Trump took office in removing federal data. So he was, a lot of the federal data was just removed from websites so people couldn't access it. There was later a court order that required it to be reinstated. And I guess the short version of the next few slides is that some of that data has been altered. And so there's not the same ability to trust government data in some ways. So I'll touch on these. I'll have a few slides on each of these topics. What agencies have had data removed, a little bit of background of data, the website data.gov and the idea of open data, some potential specific effects in different areas, a little bit about data and Doge, and some thoughts about kind of future of data collection with respect to like federal agencies and how they collect data. I like quotes, you may have noticed. So why should we care? Measurement is the first step that leads to control and eventually to improvement. If you can't measure something, you can't understand it. If you can't understand it, you can't control it. And if you can't control it, you can't improve it. So I think, part of who I am, like I think data is important, right? Being able to understand things through data. Don't expect to read these. I'll read them real quick. I just wanted to sort of show you the breadth of agencies that are affected by the data. CDC, I think, is one of the most important. The Census Bureau, the Office of Justice Programs, Head Start, Justice Department, Substance Abuse and Mental Health Services Administration. There's a little bit of detail about like the scope of what has happened to these organizations, but it's like a lot. The CDC is and the Census Bureau had more than 3,000 pages closed off. And I don't know if anyone's looked at anything federal lately, but there's now like a lot of websites will have messages that you can't trust the information here, and that we haven't been able to update this because of the democratic shutdown of the government, things like that. So there's this is going on now. The FDA, the Office of Science and Technical Information, the IRS, Nuclear Regulatory Commission, NIST, which is the National Institute of Standards and Technology, Health Resources and Services Administration, the Patent and Trademark Office, Department of the Interior, Department of Veterans Affairs, Marshal Service. So they've all had like a variety of things removed. Again, some of that has come back, but there have been some researchers that have, some of the data is archived, right? So you can sort of look and see if things have changed. So some of it has, which I'll get to in a couple slides. A little background of this website, data.gov. It was created by the Obama administration in 2009 as part of the Open Government Initiative. It was this part of this recognition that if we make more of the government's data available, that people can use it for stuff, right? And it's sort of generally a good thing. So we want to boost government transparency by making the public data easily accessible and support informed decision-making. It's a one-stop portal for federal databases from multiple government agencies. So it's a nice interface to be able to look at a lot of data sets. Part of the aim was to stimulate research, technological innovation, economic growth. And they wanted to standardize data sharing and encouraged agencies to publish the data in machine-readable formats, enhancing usability and consistency. So it has been, like, I think, a really good resource. And it still exists. You can still go there and get data. There was a period of time when you couldn't, right? It was down for a little while earlier in the year. It's definitely, if Trump were not ordered by the court to leave it there, it wouldn't have come back, right? Okay, so some specific effects in different realms. Again, I know it's depressing, but I do want to describe some of these things. So one of Trump's big changes in public health data was that he declared that sex is binary. So when you look at the data sets now, you'll see some information on the websites that says something like, in order to combat dangerous gender ideology, we have altered these data sets in these ways, right? So, I don't know how, you may have different feelings about this, whatever. I feel like, as a statistician, I guess my viewpoint on this is that I want the data to be reliable, consistent, collected in the same way over a period of time. These are the things that you need to be able to do good research. And so when you're changing existing data sets, you then have trouble. And in some ways, it may, for many purposes, it may just be annoying that now the variables are called something else. So if you're using that data for something, now you have to go and change all your code to reflect whatever the changes are, and they're not well documented. And so, if the data exists, if it's simply this change that the data exists, but it's called something different, that's annoying maybe, but you can deal with it. I do feel like, we don't want to create more barriers for doing research. I feel pretty strongly about that, right? It also is true that, as I say here, there may be reluctance by many to identify themselves as non-binary, particularly, to the federal government. And so I think that we're going to have this sort of blip, right? I think it'll be a blip. I think it'll be, we'll go back to collecting data how we did before eventually, but it makes it hard to track things over time and sort of like see trends and study the things that we want to study. So anyway, around public health, that's I think an issue. I think this also, not the gender issue, but having interruption in the way that data is collected will make it more difficult to detect disease outbreaks, to look at and study abortion and pregnancy outcomes, particularly because there may be women in some states that don't want, that information to be available. And to measure vaccine efficacy may be compromised. And part of that is, I think, again, in this data lifecycle process, right, we ask the questions that we want to ask, and if the people in the federal government that are asking the questions have particular ideology, the process of data collection is going to tend to be in ways that will skew data in that direction. Okay, so that's that. So that's, again, I'll make the slides available however I can do that if you want to look at any of the things. Around social equity, I think there will be harm to marginalized groups, especially LGBTQ+, racial minorities, economically disadvantaged. It'll be more difficult to document and study. It'll make it harder to educate people about the issues, affect public policy. And I think this is intentional. I guess in a lot of ways, there has been, I think, a systematic way in which there's been erosion of the ability to make certain arguments, right? So I guess I'm trying a little bit to be non-political. Like I have my own, I recognize I have my own bias about things. I grew up I was like, spent most of my adult life in Berkeley. I'm a long-haired professor. Like I have certain markers maybe, but I think I try to focus more on just like what are objective harms that I think are going on. Okay. So around economic impacts, the data collected by the government is used by public and private sectors to make predictions, make decisions that help the economy. I think this is especially important now that we're missing some Department of Labor data from government shutdown at a particularly, maybe inconvenient time. We don't know what's happening with inflation, cost of living, stuff like that. And it will be hard to measure what effect, if any, tariffs have on the economy. So, and in addition to that, it just is hard to, a lot of people use the federal data to make a lot of economic decisions. Okay, so around environmental justice, Trump has sort of targeted kind of democratic causes or whatever. So I think to some extent, anything that's going to provide evidence of climate change is going to have difficulty getting funded and collecting data, and people are getting fired and things like that. That data loss in particular makes it hard to identify communities suffering environmental pollution issues. There was a climate economic justice screening tool created by Biden. Trump has closed it. So there are these ways in which it's becoming harder to study and understand some of these issues. Okay, ties in a little bit with weather and climate change. We have lay off a lot of workers at NOAA that now we're not collecting as much and as good meteorological data, useful for airlines, first responders, farmers. It'll also be able to harder to predict extreme weather and document climate change. Some thoughts on data privacy and DOJ. So I talked a little bit about data privacy before. It's a little bit maybe ironic that it's been a talking point for the right for a long time. For example, Hillary Clinton's email servers, and there was never evidence that any sensitive information was compromised. But DOJ had access for a while to a lot of data, and I'm not them, but I think that if I were them, by which I mean people like them, I would have downloaded all the data that I could for purposes that I could determine later, right? It's pretty easy to monetize data like that if you want to monetize data like that, for example. And people will pay money for it, and I don't know that has happened, but I guess I'm suspicious about it. All right, so around individual privacy and national security, if that information on individuals is sensitive, that may make those individuals vulnerable to blackmail. That may include, some government workers, agents, identities of who the agents are. Okay, a little bit about the future. I said a little bit of this, but there's an erosion of trust in organizations like the census. Might make it so that undocumented people may not want their data to be collected for fear that it will be shared with ICE. So you have this, as I mentioned before, undercount problem, and that also determines federal funding. And science, trust in data-driven decision-making is undermined, especially if some of the data sets are being altered in ways that we may not be aware of. And I mentioned this before, part of this before, that part of that change is that there's a Lancet report recently that in July that showed that nearly half of the federal data sets had been altered. And the most common change was around gender and sex. Okay, so what should we do? My final thoughts. I appreciate you coming here, listening to me. Education, engagement, I think are important. Be aware of ways in which your data may be collected and used. I will say, I feel like I should use this extent to I have a soapbox a little bit here. I think it's a good time to make donations to various organizations that are trying to do things to protect data and whatever. To universities are struggling often, so we're on one, So that, and then the algorithms may be objective as kind of a takeaway, but those who implement them are not, and the data quality is really important. Should recognize when you use these things, search engines, generative AI, news feeds, that those things are biased in various ways. Okay, thanks for listening.
So I think we'll have time for maybe one or two questions.
And I can hang out a little bit longer if you want to ask me questions in a non-official way.
Thank you. My name's Frances. Question. Yeah, I wrote it down. So, is there a way to retrain my personal search engine, other than using DuckDuckGo, to not show AI summaries or to provide a second alternative to that Google AI summary?
I don't know. That may be something I should know, but I'm not aware of any way that you can like turn that off. There's another side of this that I haven't talked about, which is the environmental impact of a lot of the environmental impact of generative AI. Uses a lot of energy and water to run the models to do that. It's maybe surprising. So that is another reason why you should want to turn off the generative AI used in the search engine, but I'm not aware of a way to do that. Although, besides, as you say, changing to something that doesn't have that.
Okay, last question. Go ahead.
Oh, hi, I'm Bonnie. Thank you. This has been really great. I was curious, when I worked in market research, I was surprised how many depositions I was pulled into, and I'm curious how much you think the courts, are going to help here, and what we would need to do to educate all these, people who are making these decisions in a court of law.
Yeah, it's tricky. I do think. Part of the answer is it depends on what the judges believe and know and who they're appointed by and stuff like that, right? So that's part of it. We do live in a country where most of the people making decisions at the federal level are lawyers. So that, I think, kind of colors the way that we do things. I've actually read a few things lately about reasons why China is different than the United States that make me, honestly, root for China a little bit more than I was before, but that they're run mostly by scientists and engineers, the people in power there. So there's lots of things wrong with China, but there are ways in which I'm not sure if I'm addressing your question quite, but I do think that there are ways in which the law can help. Yes, there are still. I'm sure you're aware of legal decisions that are happening that are limiting, like I said, forcing Trump to put the data back up was one important thing. So yeah, it's not perfect, but best democracy we have, right?
Okay, let's thank our speaker, Dr. Ibser, today.
Thank you.
For a great talk.
Thanks so much.